about dark matter. This is something that I study as a scientist. I'm at TIFR in Colaba. This is one of the things that I've started studying over the last 5 years or so. I started doing my PhD in 2003. At that time I was studying something else. So this is also one of the things that I would like to mention, that as an artist or a scientist, your tastes change, and you have to make a very conscious choice of what you want to study. And hopefully I'll be able to convey to you why I'm studying this. Okay? So we'll talk about dark matter. So just to start off really slow and set the stage, this is a picture that I think everyone should be familiar with. Okay? This is a map of the region around Mumbai. Sorry? So this is the region around Mumbai, and we are somewhere over here. And when you see this picture, when you see, you readily recognize the big cities, right? Okay, here is Mumbai, probably Pune, Basudeb or something. Okay, so you know that there are people living here. There are all these lights. Where these lights come from? Probably street lights. Probably people living in their homes. What's there in these dark areas? If I ask you this question, everyone has a clear answer, right? Is there nothing out there?
Trees.
Trees, jungles. Okay. But it's not empty, right? It's not empty. Now if I show you this picture, this is another picture of the universe. Just instead of looking down at the earth, away from the earth. And you see the stars. If you look really long and on a clear day from a nice location, you can even see the Milky Way. And you see these dark areas in the middle. What's there? What's out there? Is it empty? Are there forests or trees out there? What's out there? Okay. Is it empty? We don't know. Let's take a slightly zoomed in picture of the same thing. You go in, and if you're looking at the sky through a telescope, this is what you would see, a big galaxy and all these smaller galaxies far away in the background. Now I ask you that, okay, what's there in these dark black regions? Is that empty? Still not very clear, right? You don't know the answer. And that's the mystery. For the longest time, it was very natural to assume that that entire dark space is just empty space. There's nothing out there. This is strongly in contradiction with what we would do if shown a map of India with certain regions which are not lit up by light, where we would not say that it's empty. We would say that there's something out there. But when shown this picture of the universe, our natural tendency, there's nothing out there. And this has actually happened in the history of human knowledge again and again. People have thought that the world was flat, there was nothing beyond their own little island, and we've always learned that there's something more. Just because you don't see it doesn't mean that it's not there. Okay? So this is the story of this dark part of the sky. Okay. What the universe really looks like on the largest scales. 100 million light years across. Okay. On the largest scales of the universe, this is what the universe actually looks like. Not very different from the map of India that I showed you. Okay. You see this network of lights. It's actually not an actual picture of the universe. This is a simulation. What you see in this yellow color are stars in galaxies. Okay. But you see these stars and galaxies are sitting inside this slightly hazy bluish cloud. Okay. You see that? Does everyone see that? That's something within which these galaxies and lights are embedded. You try and argue that this hazy blue stuff within which our galaxies are sitting, that's what comprises most of the mass of the universe. And that's dark matter. You can't really see it. I've colored it blue so that you can see it here. The question is, how do we know this? And then what can we do to find out about what this object really is? When I give you a piece of stuff, you can tell me whether it's made of iron or carbon or hydrogen or oxygen. Actually tell me what this stuff is made of. And if I gave you a lump of dark matter, how would you tell me that what is this thing made of? So that's the second question that address, but that's later. First we want to ask the question, how do we know that such a thing is out there? How did we know this? Okay. It's a big mystery. It's been a mystery for the last 50 years or so, maybe a bit more, maybe 70. And let's see how we came to know what it is. So again, just to set the stage, this is typically what a galaxy looks like. Our galaxy also looks like this, the Milky Way. It's 100,000 light years across. Okay, just if anyone doesn't know this, when I say something is 100,000 light years across, it means that if I shine a beam of light like this one from one end of the galaxy, it takes 100,000 years to reach the other end. Okay, so that's how big the galaxy is. But this galaxy is actually sitting in a much bigger halo.
Yeah.
Okay, over here, about 5 to 10 times larger, which we can't see. So if you see a galaxy with a telescope, you wouldn't actually see this blue part. You only would see this yellow part of the galaxy, which is the ordinary or the visible part of the galaxy. And then there is this much larger, big, fuzzy sphere of matter, gaseous looking thing, inside which the galaxy is sitting. This bigger object, and it's actually also there in the middle, but you can't see it, that is what's dark matter surrounding this galaxy. Okay, so this is the picture that I want you to have in mind, that everything in the universe is actually sitting there. It's almost like it's embedded in this dark matter Christmas tree. These are little jewels in this dark matter Christmas tree. Okay? Okay, so a little joke. It's a sad truth of doing science that you don't want to give things interesting names. You give them really boring names so that your colleagues do not chastise you for being overly imaginative. Okay, so fine. So it's dark matter. The two questions that we want to answer are, how do we know that it's there? And then, what is it made of? Okay.
Which you call it an invisible mass. It's not gaseous, it's a mass.
Yes. So I'll come to that in a second. Invisible, very, very easy to understand. We don't see it. Mass, as opposed to a gas. Gas is a statement about what state is the mass in, right? It's whether it's whizzing around very easily, or is it solidified as a lump? We certainly don't know about that. We'll talk about that later. So invisible mass, let's start. Okay, so how do we know that there is dark matter? We know that because we understand the laws of physics here on Earth. Okay, and one of the key things that we know is that you can use the motion of objects to measure its mass. Okay, so let me illustrate that point with a very simple example first. This is our dear friend, Professor Newton, and everyone I think here knows these two equations. Okay, F equal to ma, and F is gmm by r square. So this right hand side equation is the second law of motion. The left hand side equation is the universal law of gravity. What does it say? It says that there is this apple that Professor Newton is holding, and there is a force that is acting on this apple. Okay, this force is F, which will lead to this apple falling down with an acceleration given by A. That's what Newton's second law says. That there is a force acting on it, F, which will lead to an acceleration A given the mass of the apple being M. Okay, so if you just drop this apple, it will accelerate with this number A. Where is this force coming from? This force is coming because of the action of the Earth, and that's the left hand side of this equation. G is some universal constant, which we don't have to worry about right now, and the force that acts on the apple is proportional to the mass of the apple, proportional to the mass of the Earth, and inversely proportional to the square of the radius of Earth. Okay, so there's some well-known laws that Newton discovered, and with this, what you can very easily do, G is a constant. G is the force that would act between two masses of unit mass kept unit distance apart. Okay? It's just something that sets the units of the scale. The point is, once you know these equations, you can do some algebra and you can calculate the mass of Earth by just substituting different values, and it turns out to be 10 to the 24 kilograms, where I have now written down the time it takes for this apple to fall down over a distance of a meter. So I've done the algebra for you. So what it says is that if I hold an apple up a meter above ground and drop it, it takes roughly half a second to fall down, and from that I can calculate the mass of the Earth. So it's just a little bit of algebra to do, but the point I want you to take away from this is that there are these simple laws that Newton told us, which allow us to calculate the mass of the Earth without actually weighing it. Okay? We just observe the motion of something in the gravitational field of the Earth, which allows us to measure the mass of the Earth. So that's the trick. Okay? And this is the trick that we will apply again and again in different forms to measure the masses of other objects out there in the sky. Okay? Now, this by itself is a very surprising thing, and one should not take this for granted. So, the fact that the laws of physics are the same everywhere. You know, Newton discovered his laws of gravitation and of motion here on Earth. What tells you that these same laws apply elsewhere in the universe? I mean, the universe could be very chaotic and very mischievous in that it follows different rules at different places, but it doesn't do so. So there is something very nice and regular about this, which allows us to learn about the universe by applying the laws that we discover here on Earth in our neighborhood and applying them out there where we can't really go. And this is one of the most exciting things for me as a physicist. This is what really attracts me to work on astrophysics, that we learn about physics here on Earth using experiments we do in our labs, and then we use that knowledge to figure things out about things which we can't directly probe. We can send a space probe to Mars, but we can't go out there inside a black hole and do experiments there. But we can learn about things inside a black hole because we have faith that the laws of physics should be the same everywhere. And this hypothesis, rather than faith, is validated by continuous success of this method. That we've used this method again and again and again and found ourselves to be successful, which gives us this strength of belief that this method of acquiring knowledge is a valid and testable method of acquiring knowledge. Okay? So with that prologue, let's start talking about dark matter. Okay. So the way dark matter was discovered was this. This is a complicated looking plot, but I want you to appreciate what real science is like. Okay? This is what a typical scientist would look at as part of their work. What has happened here is that some experimental scientist, somebody who does observations with a telescope, has gone out there and noted down the position in the sky, so let's say the latitude and the longitude in the sky, of lots of different galaxies, and plotted them, so let's say I know that some galaxy is at this location, along this latitude and that longitude, and plot a galaxy over here, and color coded them by the velocity that it has. Okay, so there are some galaxies which are colored red, there's some galaxies which are colored blue, as you can see, and so what a person's done, an observer has done, has gone out there, looked at galaxies in the sky, made a map of these galaxies on the sky, and color-coded them with their velocities. Now there are simple rules again which relate the velocities of these galaxies as a whole with the total mass contained in this region. Okay. This is, for physics people, this is something known as the radial theorem, but never mind if you don't know the details. The basic idea is motion measures mass. We can measure the motions of these galaxies, and therefore we can measure the mass of dark matter, or all matter actually sitting inside here. Now the interesting bit is that if I add up the masses of all of these galaxies, the mass that I get is 400 times smaller than the mass I need to explain the velocities or the speeds that I'm observing in this galaxy. And this is not just true for this one example, but hundreds of examples out there. So you can go out there, do measurements of galaxies in the sky, at what speeds they are moving, use known laws of physics, and you'll find that the galaxies are moving much faster than you would expect. So that should give you some pause, and you should wonder what the hell is going on. I mean, is it that my laws of physics are wrong? Is it that somehow my laws of physics work here but not over there? You don't know. With just one observation like this, you wouldn't know, and you would be left in this very dissatisfying position. That's roughly what happens when a field of research starts. That there is this uncomfortable fact sitting out there which people are aware of, and they don't necessarily have a clear explanation for it. But then evidence builds up. Okay? There are other things that other people observe, and which can all again be explained with the same assumption that goes behind to explain this, and we'll come to that in a second. So this was discovered by Fritz Zwicky in the 30s. He was a professor at Caltech. And he observed that the mass that you needed in that region was 400 times larger than what you were seeing. So he coined this name called dark matter, tuneful matter. Yeah. Right? So he says that the dark matter greatly exceeds the light matter by 400 times. Okay? So this was the discovery of dark matter, if you will. But then there are other ways of knowing that there is dark matter. One interesting way is to look at orbits of things around other things. So we know that the Earth goes around the Sun, the cartoon, and by knowing how long it takes the Earth to go around the Sun, which is to say that knowing the velocity of the Earth, we can measure the mass of the Sun. Okay? Motion measures mass. You do that with arbitrarily different planets. I mean, this is how it would look like. So this is the distance that the planet is at from the Sun, and this is the velocity. This follows a very well-known law, which is again given by Newton's laws, and we understand this very well. If you apply this to galaxies, what you find is this, that you expect that a galaxy like this, if all the mass is over here, then the velocity of the different parts of the galaxy going outwards, it would fall down like this. Okay? Whereas what is observed is that the velocities do not fall down, they remain the same. So I have a little video here which will give you a better sense of what's happening. If you notice, the edges of the observed galaxy are moving much faster than the edges of the expected galaxy. Is it clear? So if you just use your knowledge of physical laws, you would expect the edges of the galaxy to be swirling slowly. What you observe is that the edges of the galaxy is moving very fast, almost as fast as the center of the galaxy. And this cannot be explained unless you assume that there is more mass, because this shape is governed by how much mass is there in there. Motion measures mass, and that's one way to explain it. So we have now two pieces of evidence where the motion of astrophysical objects can be explained if I assume some form of mass that I'm not able to see. Okay? But this is not all. There's yet more evidence.
We can interrupt now or later.
You can interrupt anytime you want.
Previous slide,
Yes.
because I will forget what I want to ask.
Yes. This one?
In the right side,
Yeah.
you have more mass. Okay, your hypothesis is good. But that more mass should affect the material in the center portion of the galaxy also.
Absolutely.
You should make it travel much more faster. But
Yes.
also nearly plateau.
Very nice. Very nice. Very nice. It's a very good question. Indeed, if all of the mass that was there was concentrated exactly in the middle, that's exactly what would happen. But if you take this mass and spread it around, then the outer parts would travel faster than the center.
outer part will see more mass, inner part will not see that mass.
Exactly. Excellent question.
And secondly, is it always 400 times more?
No. So indeed, I must clarify, this number 400 is very old. So this is from the 1930s. People later learned that there was a large part of the mass which was dark, but not really dark matter. There was just gas which was not ionized into stars or whatever. And so this number now is more of the order of 10 or 20. So it's a factor of 10 or 20 more mass in galaxy clusters. Right? So this fact about rotation of galaxies was discovered by Vera Rubin. This is a picture of her when she was in her undergrad in Vassar College. She was strongly discouraged from doing science by her mentors, she being a woman. But she's one of the big stars of our research.
In fact, last 2 months I just wrote to her. She completed 80. She's around 80 or
Yes, she's very old, but she's
80 years old.
fairly active.
And I must tell you that most of the discoveries in astronomy were done by women.
That's actually true. There's a large number of very, very accomplished women in astronomy.
Very.
Yeah.
Newton's law is largely based on the gravitational force. You know? The gravitational force is more, is more prevalent on Earth rather than other planets or other bodies in the universe. So how can the same laws be applied?
So, very good question. It's a valid confusion to have, and let me address that right away. So everything has gravitation. Anything that has mass has gravitation. So on Earth, you feel a strong gravitational effect because you are very close to the Earth. When you are closer to the Sun, for example, you would think that the Earth doesn't have any gravitational force on you at all. It's the Sun which exerts a lot of gravitational force on you. For example, take some other planet like Mars. Mars goes around the Sun, not around the Earth. Why? Because Sun has much more mass than the Earth. Right? So everything in the universe which has mass exerts gravitational force on everything else that has mass. This force is proportional to the mass of the object. So the more massive a certain object is, the more gravitational force it exerts. It also depends on how close you are to that object. So if you are closer to a lighter object, sufficiently closer to a lighter object than to a heavy but very far away object, the gravitational force of the lighter but nearby object can dominate. So this is just given by m divided by r square. But we know how to work this out. Does that answer your question? So we've told you two ways in which we know how there is dark matter. I'm going to tell you three more ways. Okay? So just to emphasize you that this is the standard of evidence that scientists, require of themselves to claim something so extraordinary. Okay? It's not enough that you can say something by looking at one kind of evidence. There's totally different lines of evidence which all point to the same direction. That's why we'll believe it now. Okay, so the third line of evidence is this, that there are these galaxy clusters. So these are clusters of galaxies, almost 1,000 galaxies inside this blob of matter. And there is a far away distant galaxy in the background, and we are over here. What happens is that light which is coming from this galaxy can be bent by the mass which is sitting over here. So what happens is that the light which is trying to come over this direction towards me, because there's a mass over there, has a gravitational effect, it gets pulled and then it bends, exactly like a lens. For example, this is Einstein's lensing of light. This is exactly Einstein's lensing of light. And what this does for you, it creates multiple images of this galaxy. Because you can see in this direction you will see an image of this galaxy, you can see in that direction you will see another image of that galaxy. So what this sort of lensing by intervening mass does for you is it produces multiple images of the same source. It's exactly like you have a lens out here and you put some light behind it. The light looks bigger, right? What does it mean that the light looks bigger? It means that you are seeing the light where it wasn't. Right? It's the same thing. That there was only one galaxy, but now you're seeing the galaxy elsewhere where it wasn't because the light has been bent.
Excuse me.
Coming towards you. Yes.
Why is the light bent?
Why is the light bent? Because as we discussed, gravitational force changes the motion of objects. It also changes the motion of light. This is something surprising and it wasn't known before Einstein. Einstein predicted that this must happen and then this has been observed. Okay, so this is yet another effect. Now with this, what we can do is we can measure the mass of the lens. Okay, so if we see this lensing in some galaxy cluster out there, with this we can again measure the mass of this object. So motion of light measures mass of the galaxy cluster. Alright, so let's do that. So this is a real picture. What I have done is this yellow stuff is an optical image of the galaxies behind. This fuzzy white stuff is a false color. This is the stuff that you wouldn't be able to see, but I have colored the parts of this picture where I predict that there should be mass in order to explain these multiple images. So if you see, there are these spots which look identical to each other. These are multiple images of the same thing. So what that means is that there must be some lens, somewhere over here, which leads to a duplication of this image. So by looking at the pattern of how the galaxies get stretched and how these pictures are smeared and twisted, there is a way of inverting back this information and calculating where the mass must lie and how much mass must lie in order for me to actually explain this image. Okay? So by observing the way in which my galaxy images get smeared and twisted and pulled, I can reconstruct the mass in front. Okay? And I've done that, and then I have painted that part of the sky with this grayish blue color. Now I do see that a lot of the mass actually is there where there are no galaxies or stars. For example, look at this block, look at this block, look at this area entirely. There's very little galaxies or star out there, but most of the mass is sitting out there. Okay? So yet another evidence that there is mass out there which is not shining, it is not emitting light. We can't see it, but it's there. Now we come to really advanced and things which have been done in the last 10-15 years. Okay? These are really state-of-the-art ways in which we have understood about the existence of dark matter. So I'd like you to pay some attention. This is not hard, but very, very subtle. See, when we look up at the sky, we can only see until the surface of a cloud. Right? We can't see forever out there. If there's a cloud in the middle, that's how far we can see. Why? Because light that's coming from further out than that gets either absorbed or reflected away by this obstruction in the middle. Okay? The universe is also a bit like that. So the universe, when it was very young, was very hot. Everything was ionized, so the atoms were all broken up, everything was charged. So photons were not able to travel in this early universe very easily. So light could not travel because everything was charged. Light was always scattering with all the atoms and it would get absorbed all the time. Okay? So light which is trying to come from very far away is not able to come all the way up to me. It gets absorbed over here. But there was a particular time in the age of the universe where the universe became cold enough that atoms formed and the universe became transparent. After that point, light does not experience as much scattering. The light can then travel quite easily. So there is this surface called the last scattering surface. All the light that we can see in the universe can come at best this far away. Any light that was emitted before this cannot really reach us. So this is the first light that we can observe. Okay? And this is known as the cosmic microwave background. So this light was emitted roughly 380,000 years after the universe was born. The universe is 14 billion years old now. So roughly 13.75 billion years ago, this light was emitted, and we still see it. You can still see it. I mean, in these old cathode ray televisions, it's, somebody has one still, where you see the static. There's this weird noisy pattern. Reasonable fraction of that noise you see on your old cathode ray television, that comes from that light. Okay. So this is one of the greatest discoveries of the last decade. It's called the cosmic microwave background. So let me explain a little bit more about this. See, when you're looking far away, you're looking at a younger universe. I'm repeating myself because I've already told you this in the last slide, but this is so important that this needs to be repeated. When you're looking very far away, you're looking at things which were younger, because light has to be emitted from there a little earlier in order for it to reach me now. If you're looking at things which are 13.75 light years away, you are looking at it as it was 13.75 billion years ago. Okay? So if you're looking far, you're looking at the past. Okay? So when I'm looking with a satellite, very far away in the sky, I'm looking at the universe as it was when it was younger and hotter and not transparent. So I can only look as far as the universe is transparent. So until this last scattering surface, which is this surface. This is the Planck satellite, which is looking at this surface known as the last scattering surface. Okay? This surface more or less looks uniform, because you can think of the early universe as this very hot, bubbling plasma of material which is just interacting with itself, and it has common temperature. It's like a pot of water which is roughly uniform with itself. There are little bubbles in it, there are little waves in it, and we'll talk about that in a second. But roughly speaking, it's a big liquid which is in equilibrium with itself. That's how we call it. Okay? Now, I subtract out the part which is constant. So for example, if you take a pot of water, let's say pond, where roughly speaking the surface of water is flat, but then there are tiny ripples on it. So I don't want to think about the part which is flat, because that's boring. I want to concentrate on the little ripples that are on the surface of this lake. So on the surface of this last scattering, there are these little ripples, and now I'm showing you those. I've color coded them by their temperature. So their average temperature is 3 Kelvin. So our room temperature is, I think, roughly 300 Kelvin, and this temperature is 100 times smaller than that in Kelvin units. And what I'm showing here are little fluctuations in that temperature. So the temperature on the sky is not uniform, but it fluctuates by 10 parts in a million. It's a really precise measurement. So the uniform temperature in the sky is 3 Kelvin, but it fluctuates by 10 parts in a million. Okay? It's a really precise measurement, and these are known as the anisotropies of the cosmic microwave background. So I'm just telling you these words because these might sound scary, but it's very easy physics. It's very easy stuff, which you can understand exactly with an analogy to a pond. And this is not an analogy; it's exactly the same equations. It's exactly the same thing. So if you understand, in your school how water waves travel, the same thing happens out there. So that's another thing that I want you to take away from this, is that physics is often a lot about unification. That you learn some physical laws in one context, in the context of a pot of boiling water, and then you use that knowledge to understand the universe. Okay? Or vice versa, you develop some understanding of the universe, and you can use it actually to learn something about a pot of boiling water as well. Okay? Alright. So if you take this fluctuations, and the reason that there are fluctuations is exactly the reason why there are waves in a pond. Because the gravity is trying to make sure that everything is flat. There's nice constant surface. But there is pressure, so there is light which has some heat in it, and it tries to push things around it. So it sets up this push-pull sort of competition between the forces, and because of inertia, things will oscillate. It's exactly the same thing as what will happen in a pot of water. Let's say you're heating a pot of water from below. Gravity is trying to make sure that everything is, steady. But there's a little bubble that forms because of, a little water vapor being expanded and then it explodes inside your water. This, what it means that water is boiling. And then that sets up little waves. And these waves will, travel in your pot and collide with each other and eventually die down. So this pattern of waves can be calculated in the early universe. Sounds complicated, but the physics is exactly the same as what a water is.
Shouldn't that be uncertain?
Shouldn't that be?
Uncertain, the pattern and the speeds wave from it.
Good question. So certainly when you're, let's say, boiling a pot of water, you cannot tell where a bubble will form. But you can say something about how many bubbles will form on an average given the amount of heat. Right? So we cannot make definitive statements about where something will happen. But we can make very definite statements about the overall statistical nature of things. For example, I cannot tell you your age, right? But I can say that in this room, roughly 20% of the people are above the age of 60, 80% of the people are below the age of 60. I know that because big populations of objects obey certain laws, right? So statistics is sometimes more powerful than specific knowledge of things, and that's what we use there. Good question, thanks. Alright, so we do all of that, and we make this map. Don't have to, think about what these things are. But just one quick thing is, we like these plots. Scientists love plots, and the reason I'm actually showing you all of these very technical-looking things is not because I want you to understand every little tiny detail of it, but I want you to get a flavor of what it is like to do science. That you do experiments, you come up with data, and then you make these plots, and these tell you much more than other pretty pictures of the sky. Because there's very specific, detailed information hidden in these things, which we can then express in terms of equations and match observations with theory and learn more about the universe. Okay, so what have we learned here is that there's this, weird oscillatory, curve out there. What I'm showing here on, the horizontal axis is the size of the universe, but it's an inverted scale. So this is 90 degrees in the sky here, and this is something like 0.1 degrees in the sky, so a very small part of the sky. What it is saying is that there are a lot of fluctuations at a scale of roughly 2 to 1 degree to 2 degrees. So roughly 1 to 2 degrees on the sky, there are a lot of blobs which are the size of 1 or 2 degrees. Fluctuations of that size in the sky. And there are fewer fluctuations of smaller sizes and larger sizes. So there is a specific size in the sky at which fluctuations happen. Okay? So by knowing exactly what these sizes are and how this number of fluctuations of a given size die down, one can learn about how much mass there is. Again, the motion of the early universe plasma tells you about the mass of the early universe. So long story short, this is CMB, again motion measuring mass. Just a very involved and subtle way of doing it, but nevertheless the same story. Okay, so this was my fourth line of evidence for dark matter. Okay, I'm not done yet. Okay, just one more way of looking at it. You can, this is a calculation, by the way. This yellow curve is a calculation that I can do by hand, and I can change some parameters in my theory. There are only 6 of them. So there are 6 knobs, of which I hold 5 of them fixed. There's this other knob which goes from 0 to 0.5. Approximately what it's saying is that what fraction of the mass of the universe is dark matter, and this curve changes depending on how much I assume for that matter. So if I dial that knob up and down, I can make this curve change its shape and then try to match with the observations that I just showed you in the previous transparency. So by doing this calculation, and what one finds is that when this hits roughly 0.3, the shape is right. So this is very difficult to do for a given region, but what I'm plotting here is some statistical property. That's easy to calculate once you know what you're doing, and then you can go out there and match with observations and tell how much mass is out there in the universe. And from that we know that 30% roughly of all the matter in the universe, of all the energy in the universe is matter, of which some large fraction will be dark matter. Okay, so the fifth line of evidence is the structure and the pattern of galaxies in the sky. So on the largest scales, I already showed you this one picture of how the universe looks at the largest scales. Right? There was this network which looked almost like the map of India, with the lights and everything. This is not a simulation. This is an actual observation picture. It is the Sloan Digital Sky Survey, which actually what it does, it's a big telescope which looks at all galaxies out there in the sky, makes a note of their location and their color, and just makes a map of it. So it's like a map of cities. It's the same thing. It's a map of galaxies in the sky. And it looks, there's this very weird, network-like feature, very much like how roads or rivers, run across the Earth. And this pattern, again, tells something about how much mass there needs to be. If there is much less mass than what we would predict, this pattern would get all smeared out. It would be much more fuzzy. The fact that this pattern is not fuzzy, it's kind of crisp, tells us that there is more mass and it's of a certain kind. And we'll talk about that later, but again, the motion of galaxies, or the fact that they're not moving, tells us something about how much mass there is. Okay, so this was my fifth line of
What
evidence.
is a circular scale or the HN or the
Yeah, okay. So what I have, so this is a complicated looking plot. So these hours are actually a particular direction in the sky. So you can measure directions in angles, minutes, seconds, hours. These are hours. The radial direction is actually redshift, which is in some sense the same thing as distance away from you. And then there is color, which is given by, I think in this case, I don't exactly remember what the color coding was, but I can...
question is aimed at why two patches are totally...
Oh, because we are not observing here. I'm sorry, I should have explained that. So this experiment did not look at this part of the sky, that's why there are these dark...
What we have to observe?
I'm sorry, yeah. So because sometimes what happens is that, you are observing from within the galaxy, and our galaxy looks like a big disk, pretty much. And this disk has a lot of gas and other stuff in it, and you can't look through it. It's very hard to do an experiment which looks near the galactic disk. So I would imagine, I think I'm saying this right, that these two wedges are very close to the galactic disk, so you can't make observations there. You have to look away from the disk, up and down.
This is one of the most fantastic, I think the public generally doesn't understand that with each point I repeat is a galaxy.
Yeah.
Galaxy means thousands of planets must be there.
Every galaxy has a billion stars.
Yeah.
There are a billion galaxies out there.
Yes, ma'am.
It's a rough number to remember.
And here we on the earth keep on fighting among ourselves. There's no life elsewhere. I mean, we are in the galaxy. I mean, in our own galaxy, there is a dispute whether there is life anywhere. These are billions and billions of galaxies, which astrophysics people treat it as point objects. So these are point objects. One entire galaxy.
Yeah, so every point here is a galaxy. There are a billion of them in the universe. Every galaxy has a billion stars.
And planets? Do they have planets?
And stars have planets. Typically, not all stars, but some stars do have planets. Now we have actually much better understanding of how many planets there are out there, because there are other kind of experiments not related to dark matter called planet surveys, exoplanet searches. There's a satellite called Kepler which goes and looks for these planets, And now we even have a huge list of planets which are very much like Earth, in the sense that they have the right size, they are the right distance away from their sun, they have the right temperature to have water. So I think there are roughly... I'm sorry?
She has a question.
Yes.
What's a Kepler?
What's Kepler? Kepler is a satellite which was sent by, I think, NASA, which goes around Earth and looks for other planets, not in our solar system, but in other solar systems around stars in other galaxies even. Thanks.
Wow.
That's basically
Lose the sense of
We are not looking for life at all at this point. We are looking for planets. One possible outcome of it could be that, okay, once you find lots of these planets which look very interesting, then you start asking that, could it have carbon-based life?
I think you were about to say there are roughly so many planets like this located.
Yes. So if I get the number right, about 300 Earth-like planets are already known. Almost. Yeah. I mean, I could be off by a factor of 10 here and there. By the way, this is the way theoretical physicists work. We quote everything up to a factor of 10. Okay? So, I mean, things are known to better precision. It's just that we don't remember it. So this is another thing. Maybe, I mean, there are some students out here. In school, there is a lot of emphasis on getting everything right, 1.2734. Science is not always like that. I mean, a lot of science is just, coming up with a rough guess and then verifying it with some rough
So
experiment.
this is going to be the next answer, like a question paper which is marked wrong. Somebody's going to stand up and say, but science is not like that. So,
Ma'am, I don't want you to go away with this feeling that you can do this in school and get away with it, but I would want you to, have confidence in yourself, even if you're not getting all the second decimal place things right. If you're interested in science, remember that there is a payoff 10 years down the line once you've finished your school and college and everything. Once you are doing a PhD, no one will care about your second decimal place, except maybe your PhD advisor who will scream at you to make sure that you get that right. But you can get quite far without doing all of that. All right. So here we are. So there's a whole lot of evidence for data. So that's, I think, where the first half of my talk ends. I want to tell you about one small thing which I haven't told you about. I've told you about dark matter. This matter that's out there. But there's one more thing that's out there which we don't understand. It's called dark energy. I'm not going to talk about it in this session, but it's important that you know that it's out there. So what is dark energy? So what I'm showing here schematically again are a bunch of galaxies. We live in one of these galaxies. Maybe this one. Okay? And then, as a function of time, as time evolves, we observe the other galaxies are going far away from us. Okay? So we live in this galaxy, and these galaxies go far away from us. I've exaggerated by how much it is. Also know that the galaxy looks a little bigger, because not only are the other galaxies going far away from us, even our galaxy is sort of stretching out a little bit. This effect can be muddled by other things, but what I'm trying to say is that space is expanding at a certain rate as the universe becomes older. So the universe is expanding. As a result, other galaxies seem to be going further away from us. Why have I colored it red, the other ones? Because when something goes farther away from you, when something is receding from you, its color changes. Now we are more familiar with sound. When a train goes away from you, you hear the sound of the whistle of the train, that becoming less shrill. The same effect with light. When a galaxy goes away from you, its color becomes redder, because that's a lower frequency. Okay, it's redshift.
You can see those mountains.
You can see those in?
Mountains. We're standing in the mountains away from us.
Okay, so that's a slightly different effect. No, that's because of scattering. So, interesting questions. What happens is that when you're looking at things far away from the top of a mountain, you're looking at city, for example, and the city looks yellowish or reddish, right?
That is what
What that is?
we're saying when you're looking at a mountain range,
Hmm?
if you're looking at a mountain range, the mountains must have reduced the
Yeah, that's exactly what I'm saying. So there are two things out there. One is two things going away from each other. That leads to a reddening. Two things which are exactly the same distance apart, nothing is changing. The faraway object can look redder because there is dust. So this is not dust. So indeed this is the problem. That when you're trying to say that I am seeing a galaxy and it looks redder, because it's receding away from me, you have to make that statement with due care about the effect of dust. Because dust is something which conflates this effect. I'm sorry? Exactly. The sun looks redder at sunset. So that's because of dust in the atmosphere. That can also make galaxies look redder. So we have to correct for that and be a bit more careful than I have been. Yes.
Maybe slightly away from this, but when you say the universe is expanding, it is expanding into what?
What?
What is it?
Yes. So let me come to that question just after one or two more slides. This is something that I want to address, but a bit later. Yes.
Is there uniform expansion?
As far as we know, yes. So again, this is something that will tie up with what he's asking, and we'll come to that. So let me finish this analogy. So we are living in this galaxy, and we see these faraway galaxies going further away from us. Now imagine you have a friend in some other galaxy. Let's say, instead of living in your galaxy here, your friend lives in this galaxy here. How will all of this look to that friend? So what I've done here is that I've overlaid the pictures of these two galaxies at two different times, and you see that they have gone farther away. Now let's do that for our friend in a different galaxy. So again the same picture. My friend lives in this galaxy. As a function of time, at some later time, this is the picture of the universe that he takes. Okay? Now I overlay this picture on top of this picture, because he thinks that he's in exactly the same place as before. What he sees is that all the other galaxies are going further away from him. Okay? Now this answers your question, that every observer therefore thinks that everybody else is going further away from them. And this is happening uniformly all over the universe. That's what I've tried to show you, that whether you take this galaxy or that galaxy, and I assure you that the way I've made these pictures, they are exactly the same. I mean, just blown up this picture by 10% and colored them differently. I have not actually changed anything else. So this is exactly what happens out there in the universe. Everything stretches away from each other. This is the expansion of the universe.
We're talking about dark energy.
Yes. Yeah. So this is the expansion of the universe. Now that by itself is not, this is known as Hubble's law, the fact that the universe expands. But the big surprise in the year 2000 was that this expansion was itself increasing. So if the universe just was expanding at a constant speed, then everything would be going further away from you by exactly the same distance after equal amounts of time. And so the reddening would be constant. The rate of reddening would be the same. But you see that the rate of reddening actually is increasing with time. So instead of this blue line, so what I have here on the x-axis is the age of the universe, on the y-axis the size of the universe, or distance between any two farthest objects in the universe, if you will. And what has happened is that we are here. We can't measure this path. Sorry, we can only measure this, the past, and we can measure these different curves over here. And we find that the measurement of the galaxies tells you that we don't live on this blue line, we live on this red line. The data falls on this red line, which tells you that the universe is not only expanding, but it's expanding at an increasing rate, so that you're accelerating. You're accelerating. This is something that is completely bizarre. A little bit of physics will tell you that this cannot be done by anything that we know. You can't pump in a lot of gas or energy and make the universe expand like that. Something very, very bizarre needs to happen. We don't know what it is, so we give it a name. We give it a name. That name is dark energy. Okay, it's completely ad hoc. I mean, yeah.
If the universe is expanding, does it mean that more galaxies are coming into being?
No. So this is what brings me to the next question. I think what is the universe? Okay? What is it expanding into is the question, right? So, a good way to think about it is take a rubber band. Okay? And there's an ant on the rubber band. Okay? So the ant is the universe for the ant. I'm sorry. The rubber band is the universe for the ant. Now imagine stretching the rubber band and making it larger. Nothing new comes into the universe for this ant, but the universe becomes larger. It takes longer for the ant to get from point A to point B. This is a one-dimensional analogy of a three-dimensional. So the reason we can visualize the expansion of this rubber band universe for an ant is because we can embed this rubber band universe into our three dimensions. To understand the expansion, that to accelerated expansion of our three-dimensional universe, we will have to embed this in 4 dimensions, but we can't visualize 4 dimensions. Human beings don't have that visual ability. So we can't imagine what expansion of the universe looks like. But it's exactly the same thing as this rubber band expanding into space.
No, but the rubber band or let's say a balloon which
Lives in something.
yeah.
But
So
the
where-
universe is itself. So imagine the balloon by itself not living anywhere.
So then we have to expand into.
And then it expands. So see, think of it this way, that the ant that's living on the balloon or the rubber band doesn't know physics, doesn't do experiments, they don't know about 3 dimensions. The ant only walks on the balloon. So they have no way of having this picture of a balloon living inside this room. They only know the balloon. They are seeing that, okay, I walk along this surface. And they see that this surface is becoming larger. How are you going to explain to the ant that no, you actually are living inside this 3-dimensional room and somehow you are forced to walk on the surface of this balloon, but actually the universe is 3-dimensional.
So how many
It's
dimensions?
very hard to tell the ant that.
In one of our recent talks, I think Professor K. Sheila mentioned that actually people, that there is not proof that there are nine dimensions.
Yes, these are theories, right? So in principle, you can imagine that the universe has more dimensions, and just like how an ant can be confined to walk on a 2D surface of the world, the ant never jumps, above the table, let's say. We are also somehow confined because of biology and physics to live on some lower dimensional part of a higher dimensional universe. It's possible, but so far there is no proof of that. Sorry, I know you're not happy.
I mean, if you take the surface of the earth, for example, you don't fall off.
Right, that's another good example.
Yeah, so if you're traveling in a plane, let's say if I want to go to the United States from here, so I go along a particular latitude, and if I take if I take a plane surface, for example, this is a plane surface, and if I draw the sum of the internal angles of the triangle in school is 180 degrees, but that's not true on the
On
curved
the surface of Earth, that's not true.
That's not true on the curved surface. Because you go from something called Euclidean geometry to non-Euclidean geometry, where the sum of the internal angles of the triangle come out to be more. And then you can infer, from on the surface itself that, it's curved, something.
But isn't the universe defined
Something
as
like that.
the sum total of everything?
Yes, and the sum total of everything is increasing in size.
We'll just take a word.
It's very difficult to wrap it.
They're floating.
I'm
Sorry?
Floating.
Bloating.
No.
It is a very thing. I totally sympathize and sympathize with that discomfort, because it is not an easy thing to wrap your head around.
The same difficulty is understanding the Big Bang theory also.
These things are so alien. These are so removed from our day-to-day experience that familiarity is the only medicine.
But you're saying in terms of physics, it's understandable and it's answerable.
Yes. So
Yeah.
we know the equations, we understand the equations, and see, I could give you a slightly speculative answer, and then maybe you'll be happy.
Please.
Okay, so there are. So this, whatever I've told you so far is, canon. What really 100% of scientists will agree on. Now I'll tell you something that 10% of the theoretical physicists will agree on. There's something called the multiverse. So, okay? So essentially what it says is that our universe is a little bubble in a much bigger thing where there are many, many universes, but they are expanding away from each other faster than the speed of light. Why that happens is a complicated story. So you will never actually see anything beyond your universe. And now you have an answer for what the universe is expanding into. Okay? So, but this requires appealing to certain untested ideas, which I was trying to avoid. But this is not a satisfactory statement.
You know,
Expanding into dimension.
another thing, small example is if you take the grill, take that grill outside, you know, and if take that is 1 centimeter, your ruler, 1 centimeter, 2 centimeter, 3 centimeter, and say next day you're woken up, and that ruler, that 1 inch has expanded. The 2 inch also will expand by the same way. Your ruler will become so big. Everything around you will expand in the same manner.
Correct.
You won't know that you've been expanded, but something called as a scale factor. You say that it has.
How much has it?
Yeah. How many times it has grown into.
So you are summing up expansion by dimension, not by quantity. Universe is expanded by physical size,
Yes.
not by the tonnage.
Yes. The total amount of energy in the universe does not change.
But doesn't that mean like, there will be a time when we expand so much that the energy everywhere will be,
So that's what I'm coming to. So if the universe was just expanding by itself and there was nothing else leading to it, you would expect that the energy density in the universe would go down. But the fact that the universe is expanding at an accelerating rate actually tells you that not only is the universe expanding, there is something that is creating energy, keeping the energy density of the universe the same at all times. So when you take a box and make it 2 times larger, 8 times more energy somehow gets created inside this box. This is dark energy. That's why this is so bizarre.
So energy is increasing.
Yes.
What it?
Yes.
But dark matter.
Energy density is staying the same.
Good.
Yeah.
So dark matter also is increasing the same energy?
No. So this is what I wanted to. Give me 1 second to finish answering that question. So this feature of the universe, that the universe is accelerating, which means that there is energy being created per unit volume, which is keeping the density the same at all times. This is a very weird feature because standard physics tells us that energy is not created out of nothing, but somehow the universe requires this. So we give it a name. We give it a name called dark energy. This is very, very bizarre. In equations, there is a way of understanding it. There is something called the cosmological constant in Einstein's theory of general relativity, and it's a thing that is consistent to write down mathematically. So we know that mathematically this is okay, but physically we don't understand what this object is. We have no intuition for it.
Let us believe it for a moment. You know the rate of expansion, density is same.
Yes?
So rate of increasing dark energy can be told.
Yes.
What is that number?
That number, I could tell you that
You guess a
number.
number. You are good in guessing.
No, but I can tell you that number, but I'm trying to think what units do you want to know that number in. That number is roughly...
Percentage is it?
No, it's such a large number that you will realize why I am stumbling.
You tell percentage.
Yeah, give me a second. So, the amount of energy that is going in here is roughly 30 orders of magnitude larger than 100 times the mass of the proton. Okay? So, these are weird units.
Okay, sir. You are flattering me. I will like you.
No.
You come to percentage. I know you want to understand the percentage.
So it's roughly, let's say, in terms of mass of the proton, which is...
No, don't do that. I will be lost anyway.
You want the total mass of percentage of the whole universe?
Whole universe.
70%. Okay, that's a much
No,
easier.
there is total quantity.
Yeah.
Expansion per unit time, per second, per day, per year.
That changes, that depends on when you are looking at it.
Rate of expansion.
Give me 1 second. I think what you are asking for is rate of expansion.
That is about 71 kilometers per second per megaparsec. So, something.
I'm glad that there is a lot of enthusiasm about this. Now this number, how much of the universe is dark energy, energy depends on when you are asking this question. Okay? If you ask this question long ago, when the universe was very, very young, when the universe was very small, then the total amount of dark energy would be very small because this extra energy has not been created yet. Today, that the universe is 14 billion light years in size, a lot of this dark energy has already been created. Right now, this dark energy comprises roughly 70% of the universe. This number was much smaller at an earlier age, close to zero even.
Okay, and also earlier age is 14 billion years.
Yes.
So, whole quantity today, plus the other percent, you have 14 billion years.
Yes.
So, you get some percentage from
Yeah,
some
so
number.
it's
Is
a number.
it negligible percentage?
No, it's right now, in the present day universe, this is not a negligible percentage.
Say 1% of the whole universe is getting created per year.
70% of the whole universe
Is
gets
dark energy.
is dark energy, which doubles itself in every unit of time known as Hubble time.
What a time. That also okay.
That is roughly 14 billion years ago.
14 billion is getting doubled.
Yeah, right now.
Yeah, it is getting.
That's something.
Okay, good. So you wanted to know this, that the dark energy will roughly double itself every 14 billion years at this point in time.
So we can
Right. So this is what I wanted to sort of bring the first half of my talk into, is that there is this completely confusing and bizarre aspect of the universe, which is the universe is expanding at an accelerated rate, which is something called dark energy. This is not what I am going to talk about. Okay? This is something which is somewhat beyond my expertise. I mean, I know about it, but I've never worked on it per se. That's dark energy. The reason why I have not worked on it is because this, at least in theoretical physics, is thought to be more of a problem with gravity than a problem with particle physics. And my training was in particle physics, and I started moving from particle physics towards astrophysics and cosmology. So this is one more step further away for me. So I confine myself to the study of dark matter, which is roughly 27% of the universe, a quarter. And ordinary matter, all the stars and the galaxies and all these things that you see, is just 5%. Okay? So the universe that we see is just 5%. There is 27% more of the universe which is exactly like the stuff we see, but does not have light. It does not shine light.
Why?
I'm sorry?
Why?
Why? That's the second part of my talk. Right now, this is what we have established from observations. So 27% dark matter, 5% ordinary matter, and then the rest is dark energy. So we're going to talk about dark matter today. And let's see where we are. So you answered this question, how do we know dark matter exists? Because of all these different lines of evidence. I hope I have convinced you of that.
Yes.
And then the second part, can I go on a little bit more? Yeah.
Yeah, because there's no deep brain. Nobody is giving us speech. So you have to
All right. So
Just before we move on the next topic, this dark energy you said is expanding, right? So in another 14 billion years ago, it
Yes.
becomes towards 100% because it was
yes,
negligible.
all these other pies will shrink further,
So
and
what
the
is
universe
going to
will become more and more dark energy dominated. Yes.
So it can be at see from 14 billion years it's become 68%, which was
Yes,
negligible earlier.
yes.
So another 14 billion is going to be 100%.
No, the rate is not linear.
Or maybe
it's
something
exponential, but go on.
approximately like
Yeah.
was 100. So what will happen then?
So what will happen? This is a very important question, and it's a very depressing answer to give. What will really, as far as we understand, our universe will become a very lonely and cold place to live in over time. So I think what will happen, we are living in a very interesting time where we can see all these other stars and galaxies. 10 billion years later, all these other galaxies and stars will be so far away from us that their light would never reach us. So we would be living in this completely dark universe where there is nothing in the sky. The sky looks completely dark at night, except perhaps the sun which is nearby. So all these other faraway objects, like galaxies and faraway galaxies, they would have gotten so far away from us, so highly redshifted that we wouldn't be able to see them. And so we would be living in a very, very depressing, era if we were living 10 billion years later. And imagine human beings trying to do science in that era. They wouldn't even know that there are stars out there that you have to go and measure. I mean, can you imagine? So, if let's say our civilization gets wiped out and then another new civilization takes place 10 billion years later, they would have to learn all of astronomy and cosmology from scratch, and it would be much more difficult for them than it has been for us. This should give you a sense of why it is so hard to make sense of the universe. Because the universe ties our hand behind our back in many ways. We don't have a second universe with which we can play. So it gives us these very specific conditions where we live in, and then we have to study this universe that we live in. It's very hard, but still we make progress.
Aren't we moving away from the sun as well?
Very slowly. So to finish off this question and join with you is, things which are very far away are more directly affected by this expansion of the universe. Things which are gravitationally bound, things like an Earth and the Sun together, their separation is not strictly given by this expansion of the universe. They can remain bound together. So it's not that as the universe expands, let's say if I live for another 10 billion years, that my body would become 10 billion years. That there are other things come into play. The fact that my atoms have charges, electric and magnetic forces that they bind together, that far exceeds the impact of gravity. And so my body, roughly speaking, would remain the same, whereas the universe would expand. So one has to take with a pinch of salt when I say that everything is going far away from each other. Everything where gravity dominates is going far away. When other forces like electromagnetism come into play, then you have to be a bit more careful. Okay?
Like you said, dark matter is something which has mass, but it doesn't have its own light, right?
Yes.
So similarly, it's with like moon, it has mass, it doesn't have its own light, but then it reflects the light of the
Very
sun.
beautiful.
Very nice.
So then,
Very nice.
Yeah.
So you are asking that why can't this dark matter be something like the moon? Right? Good. But you see, the moon does reflect light. Okay? So you can see the moon. The moon is not really dark.
So dark matter absorbs the light.
So the question is, what does dark matter do? Does it absorb the light, or does it not interact with the light at all? It just makes light fast. We don't know.
We don't know.
Probably the answer is that it lets the light through. Absorption, in principle, one can come up with some very bizarre particle physics model of dark matter where this would happen, but probably wouldn't work. Okay.
Have we sensed any dark matter nearby? I mean, like in our solar system?
No. So we have no evidence for dark matter in the solar system. Solar system is too small a scale over which we can do sensitive
So we can't
experiments.
expect any physical experimentation with dark matter.
We'll talk about that. Because we are not bound to just do experiments with dark matter in the solar system. We can do experiments with dark matter in the entire galaxy or even farther away, as I will talk about. So that's the second part. So let me wrap up this first part with something which I find kind of amazing. So this is a picture of a supernova, a star which is roughly, in this case, 20 times the mass of the sun. These stars which get old and then run out of fuel, and at some point of time they explode at the end of their life. These are called supernovae. And the answer to the question, what is the universe like, what are we made of, would be stardust if this question was being asked 70, 80 years ago. And everything here, the atoms in your body, they actually come from these stars. Because there is no way of making carbon or oxygen anywhere else except these stars. When you say that, I want to make something, let's say a golden crown for a king, that gold itself has to be made first. Where does that gold come from? The gold comes from the star. Same for the atoms of carbon and oxygen in your body. So almost everything except hydrogen that we see around us was cooked inside these stars. These stars exploded, spewing their guts out. These gas of elements condensed again, formed new stars, exploded again at the end of their life. This kept happening a few times until this gas at some point of time condensed, formed the sun, the solar system, planets around it, and on the planet Earth, us. So this is the story of human beings, if you will. We are, things which were cooked out there in stars, And now we have gotten to a point where we are studying stars. Okay? So it's a very interesting situation where the universe has figured out a way to study itself. Okay? And this should give everyone some pause about what is our place in the universe. This is a big fundamental question that we all ask, that what is the purpose of human life? The purpose of human life, if you ask an astrophysicist, is for the universe to know itself. We are an agent that tells the universe what it is doing. Okay, so we live in we are a very tiny part of this very big universe, but we are a very important part, because as far as we know, we are the only way in which the universe can know about itself. So we are in some sense the conscience of this. Okay, so now the second part of the talk. What is this dark matter? Okay, what is dark matter? This is a very interesting question, not simply because we don't know the answer, but because this forces two completely different set of people to talk to each other. Very similar to what's happening here. That I think there are people from the theatre community who are excited about learning about stars and science. It is exactly similar. At some point of time, the astronomers who are looking out there in the sky realized that there was something funny going on, dark matter, which I have told you about. And they didn't know what this was made of. What are the atoms of dark matter, if you will? And so they talked to their particle physics friends who look at things which are smaller than people, and they need to talk to each other. At some point in time, they started talking to each other. I personally am, also part of this community where, essentially I am not a full astronomer, I am not a full particle physicist, although I was trained as one. But large part of my job is translating between these two communities. So there are people who are pure astronomers, astrophysicists. There are people who are pure particle physicists, Sridhar being one, who gave a talk last week. And my job as an astroparticle physicist is to take these two bodies of knowledge and bring them together and translate things across so that they can understand each other. And often what happens is that people have missed important insights in each of these fields because they don't know about the stuff that's going on out there. So that's our job. So we believe in arbitrage. So inefficiencies in the market on both sides, we exploit them. Okay, so now coming to your question, why can't dark matter be something like the moon? Indeed, these things are what would be called massive astrophysical compact halo objects. Very weirdly named thing, but if you realize why this has been done, because sometimes physicists can be funny. Okay? So these are called machos. And opposed to a different example of dark matter called WIMPs. So there was, I'll talk about WIMPs later, but this sort of object, so any astrophysical object which does not emit light, so which does not have a temperature high enough that it ionizes the atoms and emits light on its own, that's a macho. Okay? So why can't dark matter be this sort of an object?
So what is physical, not a macho?
Not a macho. So my claim is that dark matter is not a macho. So people initially thought that dark matter could be made of lots of other planets or old neutron stars or old white dwarf stars or even black holes, because black holes don't emit anything either. But turns out that this doesn't work for various reasons. For one, black holes are too compact and they wouldn't form this very diffuse sort of shapes that I have been showing you before. They would be very, very granular. So that doesn't work. These are too few in number, old white dwarfs or old neutron stars. We know how many stars form on an average, and so the numbers don't work out for these. These are actually planets, Jupiter-sized planets, which have been found by this satellite called Kepler. Okay? So we now know that there are many of these planets, but still there aren't enough. Yes.
I understand all these three, but the black hole, I don't understand what's a black hole. I mean, it doesn't let any light pass through.
Yes, it's so unfortunately talking about black holes will take us very far away from what we want to talk about today, and it's a very long story. But for our purposes, black hole is just a whole bunch of matter which has been squished to a very small size, so small that it has densities which are unimaginably high. Let me not even put a number to it. The interesting thing about it is that light cannot escape the region of influence of this very dense object. What it means is that there is this very dense object out there, and then there is an imaginary sphere around it. It's called the event horizon. Any light that enters in that region of influence cannot come out anymore. So what will happen is that if there's a black hole out there in the sky, there would be this, big circle of the size of its event horizon, inside which we will see nothing. So that's a black hole.
So light does not penetrate.
Light does not. Light just goes in and just gets absorbed in the black hole. It cannot come out.
Okay.
Is that not a part of the dark matter? Black hole?
This is not. Right. So the point was, could all of dark matter be made of black hole? The answer is no. That black holes, as I said, are very compact and very tightly bound objects. Whereas dark matter that we showed in all those pictures, it needs to be much more smeared out and smooth. So that does not work. There's a very technical way of saying this, is that dark matter doesn't show as much micro lensing or lensing as you would expect from matters. This bending of light would be much stronger if it was tightly bound like this. But we don't see that. Okay, so the micro lensing constraints rule out matters. Another very interesting thing is that we can observe collisions of galaxy clusters. Okay, so this is a montage of 3 different pictures. Let's run through them after everything has come together. So this is the picture as you would see it, in the sky, just galaxies. These red blobs are what you see using an X-ray telescope. Okay, the blue is what you would see using the lensing signal, just by measuring the things. So what does all of this mean? Can be confusing, but what it means is that when you see just with naked eyes, not just with the optical telescope, you see these stars. Okay? But most of the mass is not here. Most of the mass is given by the lensing signal, which is in this blue blobs which will appear here in a second. Yeah, these ones. Okay, most of the matter is in here. But when you look at it using an X-ray telescope, which basically looks at ordinary matter, it gives you this pink blobs out here. Okay, and then there's this sharp feature here. So what the hell is going on? Very confusing, right? So let's look at this still picture of the same thing. What is happening is that there were 2 galaxy clusters which collided with each other in the sky. And the dark matter part of each of these galaxies went through each other. Whereas the ordinary matter part, which is shown here in this gas, hit each other and collided and ionized itself and produced these shocks. This is exactly like the shock wave that is produced when a supersonic jet goes through the air. It's called a bow shock. So what has happened is that there was this small but fast galaxy cluster which went through this other bigger galaxy cluster, and in the process created this big train wreck. Okay? Yes, this is a picture of what has happened. This is known as the bullet cluster. There are another, I think, the order of 10 or 20 such examples known which we have observed on galaxy cluster collisions. Okay? So this is the picture, I think, which appears on the invitation page for today's session. This is the bullet cluster. In my opinion, this is one of the most striking evidences for dark matter because it shows you many things all at once. It shows you that most of the matter is out there which is completely removed from the ordinary matter part. It shows you that it forms a blob because you can lens it and you can measure exactly where it is. And it shows you that it goes past each other.
So, you used the word collision of galaxies. But you also said the galaxies went through each other.
Very nice, very nice. So let me make this more precise. What is a galaxy? galaxy is a bunch of stars, which are going around each other, and then there is some gas in this galaxy. Stars are point objects in the galaxy, and then gas is something which is more diffuse, and it's like a little pudding inside which the stars are the raisins. Okay. Now there are two such puddings which are colliding with each other. The weirdness of this pudding is that the pudding goes through each other. The pudding of the ordinary matter does not go through each other. The raisins don't hit each other because they are very nicely separated from each other. So the stars go through, the dark matter goes through, but the ordinary matter, which is the pudding part, that smashes against each other and creates this strain. Okay? So there's something very weird happening here. The stars go past each other, the dark matter goes past each other, but ordinary matter, which is gas, bangs against itself. Okay? Ordinary matter? Yes, so there are some part of the ordinary matter which forms stars and things, and they go past each other, but the part which is gas does not. That collides with itself.
So you mean like this dark matter neither interacts with itself nor with ordinary matter?
To the extent that we can observe. So what this allows us to do is say how much does dark matter interact with itself or with other things. These sort of specific statements about what do I mean by how much, what numbers should I attach to this. This is the job of an astroparticle physicist like me. Take a picture like this and translate it into measurable, quotable numbers about what is the level of interaction between dark matter particles. So now I can give you that number. That number is that dark matter particles interact with each other with roughly the same strength as two neutrons. Now we know how neutrons interact. There are things which you can measure in the lab. So if I assume that the dark matter mass is the same as a neutron, then their interactions are the same as a neutron or less. Okay? If the mass changes, then you can appropriately scale this number. But let me just state this as a simple answer, that roughly as much as a neutron. That's the maximum that dark matter is allowed to interact with itself. With ordinary matter, it's allowed to interact even less. Why? Slightly more tricky explanation, so I will skip that. But we can attach these numbers by looking at pictures like this. Okay? Alright, so this brings us to the question of what is dark matter? Because we can make all these measurements and yet we don't know what this object is. It would be the same thing as what scientists were going through in the 17th or the 18th century, where they knew roughly about the properties of certain kinds of matter. There was something which shines, and there's something which is a liquid, there's something which when you set fire to it, it burns. But we didn't have a clear understanding of why certain kinds of material had the properties that they did. Why is it that metals were shiny? Why is it that metals were shiny? Why is it that certain things caught fire? Why is it that, let's say, certain things like mercury were liquid? We didn't understand it, and we understood it because of atomic physics. We understood quantum mechanics and atomic physics, which led us to a microscopic understanding or a particle physics understanding of the substances. Right? This scientific journey has not yet started for dark matter. Okay, so now this should tell people in the audience how far we have to go in science. That we have understood 5% of the universe out there. There is this 27% of the universe for which we don't have a theory. We don't have a framework. We don't have the set of equations needed to explain their nature. We know certain things about it, but we don't have a complete theory.
That's because we cannot physically interact with it.
Yes, but now we have to figure out how we are going to circumvent that problem. And the other, dark energy, is a much bigger mystery that I'm not even going to touch upon. Okay, so let's take baby steps first. Dark matter, which at least I know it clusters and makes blobs. So now I can go there and do an experiment on it. We'll see how.
There is a term called origins of Apollo, where after we did the moon landing, and these all Elon Musk and all they want to go to Mars and all. So they felt like betrayed because after the moon landing, there's been no kind of major
big mission. Yes.
big news kind of.
Yeah, but I'll show that in order to do these experiments, you don't actually have to go to a dark matter. That's one of the beautiful things that which I think emphasized at the very beginning. Newton's laws, or laws of physics in general, gives you a very powerful way of doing experiments at a far away place without actually going there. Because you trust implicitly that laws of physics are the same. There is a very strong reason to believe that. And so by using this fact, you can do experiments far away. And that's the beauty of astroparticle physics or cosmology. You're not actually going to go out there in a galaxy.
That wouldn't be so much interesting for the layman. Why the moon landing is interesting.
Sure.
I mean,
But it's
it
as
would be
interesting
great
as...
for you guys, but not for us.
We'll see. We'll see. So for example, a couple of weeks ago, we discovered these two black holes going around each other. It was detected using gravity waves in LIGO.
Yeah.
I think we didn't have to go to that black hole, but still the public was very excited about it.
Right? Investigation.
So you don't have to do Interstellar to know about black holes. Okay? You can know about black holes sitting here. I think it's equally bizarre and interesting. What LIGO did, they built basically a big, arm of a laser which was kilometers long, and they could measure how. So there was this, two mirrors which were placed roughly a kilometer away, and they could measure the shift in the distance between these two mirrors by a fraction of a width of a proton. Okay, that's the level of engineering. We can't get a windowsill right. So that's a totally different level of frustration, but it's also equally encouraging that we can, as humankind, indulge in such quality engineering.
Professor, you gave two statements earlier, 15-20 minutes back, that dark matter is not increasing like dark energy.
Yes.
Just now you told, a minute or two back, that we nearly don't know anything about dark matter.
Yes.
So I'm assuming your earlier statement is questionable.
Why?
Your earlier statement, the dark matter is not increasing like dark energy. That is your original statement of 20 minutes back.
Yeah.
Now you told.
We don't know anything about the particle physics of dark matter.
But still you are holding the statement in
that it does not increase in size, yes.
Can you go into details of why
Yes.
it's not increasing and how you know it's positive that it's not increasing?
Right.
What anything you are saying,
Yeah.
which you don't know anything.
Very good. That's a very valid question. How do we know that unlike dark energy, the amount of dark matter is constant?
Please.
That is because we have done these observations at very different epochs in the age of the universe. So we have done some measurements when galaxies are forming, that was this cosmic structure of galaxies. We have done experiments on the cosmic microwave background, which was when the universe was very young. And we can do experiments on galaxies which are very, very new today. So we have these three very different times at which we can do experiments on dark matter. And from a comparison of this data, we find that the amount of dark matter has not changed.
And that the measurement is only by gravity.
Yes.
Gravity measurement.
Yes. Yes. So in principle, what could be happening is that this dark matter could be some particle which decays very, 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 very slowly. And so far, for 14 billion years, it has not decayed. But it could be that it now starts decaying. So all of these ideas are allowed. Just that we haven't got to a point that we can test these.
So still I want to trigger you. There's something like uncertainty band in experiment.
Yes.
The graph
Yes.
is so uncertain.
Yes.
In your statement of dark matter does not increase, what is the uncertainty bandwidth?
Yes. So the uncertainty bandwidth is 10 to the power minus 24. So we are very precise. We are very precise. But we, scientists never say no. It's possible, but within that small error. Okay.
Sir, you must not forget that when they say, when astrophysicists say that they don't know, it's the word, there's a loss of language. Also, you must remember that we are bound by language, particularly in quantum mechanics.
No. So here I'm not talking about anything about mechanics, but when I say I don't know, it means it's uncertain.
Yeah, but it's pretty,
We know some things, but often we like to err on the side of caution.
pretty much.
No, I would much rather say I don't know
Yeah.
than tell you something that's wrong.
That's right.
I'm going to play spoiler
Yes.
and say we should move on so that
Yes.
we can hear your whole story and then come back to questions later.
Okay.
Because
Okay.
we don't have
So I'll
time.
try and wrap up in another 5
No,
or 10
you take
minutes.
your time. It's just that
Okay, but we can talk more.
Yeah.
Alright, so alright, so now we are going to really take on this question head on. Which particle is dark matter? We know that dark matter is not made of these whatever blobs of planets or dark matter, but could it be just some particle in the standard, whatever we know about in particle physics? And this is a list of particles that we know of, and just cut a long story short, for various reasons we know that none of these particles can be dark matter. Because some of them are massless, some of them decay away faster than they should, in order to give dark matter. Some of them interact too much, some of them are too light, these things called neutrinos. In principle they could make dark matter particles, but the only thing that spoils it is because they're too light, and then what it does is it travels a little too fast and smears out the galaxies. So the fact that we saw the galaxies were very crisp looking, that kills the fact that neutrinos could be dark matter. Otherwise neutrinos would be perfect. So it's not that we were totally off base, but somehow things don't work out with all the particles that we have discovered so far, including the Higgs boson, which decays away, so can't be dark matter. Okay? So all of the particles that we know of, so I just want to sort of skip over this stuff. Basic point is that it doesn't work. Okay? And so this is an exciting thing for a particle physicist. We revel in chaos. There is a very beautiful article by one of the stalwarts in particle physics. Stephen Weinberg is a Nobel laureate. Stephen Weinberg wrote an article about 15 years ago when I was in grad school on 4 golden rules for scientists. So in those 4 golden rules, he gives advice to a young graduate student, a PhD student, on how to do well at research. And he very liberally draws from his own experience as a graduate student. By this time he is already a Nobel laureate and an established person, so he can do whatever he wants. So he says 4 golden rules. The first one he says is that don't assume that you will have to learn everything first in order to do research. So you learn as much as your advisor thinks that you should learn, and then start doing research. And then you will learn on the job. And I think this is true of everything. Nobody learns swimming by reading a book. Okay? So this is true of science as well, that the way to learn about science is to do science. So that's his first lesson. The second lesson he talks about is that go for the messy stuff. While you are already in the swimming pool without knowing how to swim, trying to learn how to swim, aim for choppy waters. So very bold advice. Like you don't know how to swim, but go where the currents are strong, because if you swim in the baby pool, you will never win any Olympic medals. So that's the philosophy, that if you want to discover something new in science, you have to go where things are completely chaotic and messy. Don't work on things which are very, very well understood. Because it might feel very nice to understand things very well, and you will have this intellectual satisfaction, okay, now I understand general theory of relativity. But you have not discovered anything. You have only processed what other people have told you. That is scholarship. That is not research. If you want to become a researcher or a scientist, somebody who discovers something new, it is much more important to go and do something which is messy and dirty and not even that precise. Just do some slipshod job rather than something perfectly but which is well done. That's the second piece of advice. So that's what I wanted to come on. But the other 2 pieces of advice, just for completeness, one is that don't be afraid to waste time. Which I'm not. That's why all these completely irrelevant stories. And the reason is because if you always think of your final goal and are always too focused, you will miss out on a lot of opportunities to have fun, and you will also miss out on a lot of opportunities to discover something new that you had not thought of. So it's important to explore laterally. And the fourth one is learn about the history of science, which no one typically emphasizes in science, but it's very important. Because unless you know the history of what your scientific ancestors have done, it's very hard to get a real sense of what you are doing, why you are doing, where you are doing. Okay? So these are the 4 lessons. I think they are very important.
By whom, sorry?
Sorry?
Lessons from?
Lessons from Stephen Weinberg. These are called 4 golden lessons. There's a very nice, it's a commencement address that he gave somewhere. I forget the name. Okay. So, which brings us back to this point number 2 of Weinberg. Go for the messy stuff. That's what we do. And as a theoretical physicist, we are in this messy zone now. That we know that there is dark matter. We need to know what particle it is, and we have no clue. So what we do is we speculate. Unadulterated speculation based on known physical laws or allowed extensions of known physical laws, so that they remain consistent with all known observations. So it's speculation, but with very strict constraints. You cannot imagine whatever the hell you like. You can, but if it contradicts experiment, it's not science anymore. After that, it becomes something which is just a story. Good science starts out as speculation or hypothesis, more respectable word for that. It gets tested, and then if it survives, it remains a hypothesis until it gets tested so well that at some point of time you start saying that, okay, this is a model or this is a theory. This has been tested so well that we haven't found anything that contradicts it. Maybe there is a good reason to now believe it. All of this is based to some extent on subjectivity of human beings. Science is not as objective as the common. There's nobody comes and gives you a rubber stamp. This theory is now proved. No. Science also evolves by consensus. It evolves by scientific consensus, which is built by repeated testing of a theory using observations. Okay? So this is the basic structure of doing research, and it starts by guessing. We guess something and then we go and test. So these are a lot of guesses for what dark matter could be. So could be axion, some particle, some other particle called WIMP, weakly interacting massive particle. They're all different theories. I don't really want to tell you about all the different particle physics theories of dark matter, partly because it's very technical and doesn't serve a purpose, partly because there are just too many of them and there is no point telling you about a few of them which may not even be correct. It's enough to know that there are literally hundreds of ideas for what dark matter could be. Okay? But they all fall into some rough categories. It's like different implementations of some very rough ideas. So one rough idea is that dark matter is some yet unknown new particle which has some mass, let's say 100 times the mass of the proton, and which has very small interactions with everything. This idea is called a WIMP because it doesn't do anything to anyone. Weakly interacting massive particles. Then there are these other particles called axions. These are very, very light particles. These are particles which have a fraction of the mass of the neutrino, but for some very cute reason, they don't lead to the smearing out as you see in neutrinos. They can also be dark matter. Why are they called axions? Very interesting story. These were postulated by a guy called Frank Wilczek. He's also a Nobel laureate at, I think, right now in MIT. Frank Wilczek postulated this particle with Weinberg, of course, Weinberg-Wilczek axiom. And the reason why he called it an axiom was it cleans up a problem in some other area of particle physics, something called the CP strong CP problem. And if you introduce this particle, that problem goes away. So this is how we function. We know that there are two problems. There is dark matter problem and there is this other problem. And I come up with this hypothesis that let me hypothesize that there is this particle axion. I am doing it in order to solve this strong CP problem. But as a byproduct, I explain dark matter. This is a good theory. Because, this is part of a good theory. Because A, it is in some sense elegant and minimal. That I have tried to solve two problems with one idea.
It's like script writing.
Solve two plot ends. Excellent. Yes. So Actions clean up a problem, and there was a brand of dish available in the US at that time known as Axion, so that's it. Okay, so this is the rough approach we take to model building in dark matter. That we want to solve some problems in a minimal fashion, and then comes the second part of model building, is that whatever you predict should be testable in some way. That's a really good thing. But if you predict something which cannot be tested in any way, that's not fun. Because then that pretty much goes into the realm of unbridled speculation. Scientists like speculation, but speculation that can be tested somehow. So now is the testing part. So I will skip this entire part of how we speculate. I hope I have given you a rough sense of how we speculate. But let me quickly now get into this part of how we test our speculation. This is the more important part. Okay? And that job is done by people in our community called experimentalists. So they build experiments which test these ideas. Okay? Often for these dark matter experiments, in a very counterintuitive sense, you have to go deep underground in a mine to study things which are out there in the universe. And I'll tell you why. What's going on is this, that these are, not to scale, just to explain something, how do we look for dark matter? Particle nature of dark matter. So there is this class of dark matter particles or models that we have speculated about, called WIMPs, where we predict that there should be an interaction with protons, atoms in our stuff, silicon. So you make a block of silicon, and you expect that the dark matter particle, when it comes and hits this block of silicon, it will lead to this silicon atom, to be disturbed by it. And what happens then? It moves and it creates a little bit of heat or light, and then you try to measure. Now you would ask me that, well, but you just told me that dark matter doesn't interact with anything. Yes, it doesn't interact with anything at a certain level. We now have to build these experiments to a precision which is better than that level, and look for that residual thing which is in that uncertainty range, and see if we can see dark matter interactions. Okay? So just to reiterate that, dark matter may or may not have interactions with ordinary matter, but a large class of dark matter models predict a certain weak interaction. That weak interaction is so weak that we would not have detected it until now. But we will build experiments which are more sensitive and look for this weak interaction. So what happens then is that this is Earth. There is some dark matter out here in the galaxy. These particles are moving around all which way. One of these particles, which is out here, can come and hit my proton in my detector. In doing so, my proton ricochets away. This, and the dark matter particle goes away. I can't really see anything about this dark matter particle, but the fact that my proton was kicked out by something tells me that there must have been something that kicked it out. Now, there could be many things which disturb the protons in my experiment, which is why I need to go to a place which is very quiet and undisturbed by other things. That place is typically the bottom of a mine or under a mountain. Why? Because all other particles have more interactions, and they get absorbed by the mountain above me. Only very weakly interacting particles like dark matter and neutrinos, they can penetrate through the mountain and hit my proton in the detector. So I go to this place which is very sterile, very shielded from the rest of the universe, and using very precise experiments, look for these protons being kicked out. So that's the strategy. Okay?
But even if it could be neutrino also.
Yes, it could be neutrino.
How different is neutrino and
in a second. So it could be a proton, or it could be one of these other particles called neutrinos. Now with neutrinos we know how many of them are there. So we know how many of these kicks will happen because of neutrinos statistically. If we start seeing more kicks than that, then you know that there is one more source of collisions in my detector. Gives you a hint for that. If you have caught my drift by now, I wouldn't claim discovery with just that. I will need more evidence. 5 different experiments seeing the same thing at the same level, with the same mass for the dark matter particle, with the same interaction. Then I will say that, okay, yes, we have it. So there is this whole process of building up many experiments looking at the same thing. This is what's going on right now. So this is again some complicated plot. Okay? But what I'm showing here on this horizontal scale is the mass of the purported mass of the dark matter particle. We don't know what it is. So we make these plots to summarize our level of ignorance or knowledge about dark matter. So on the horizontal scale is the possible mass of the dark matter particle. On the vertical scale is how much it interacts with the proton. Okay. Now all these different lines that you see are the level to which a certain experiment is sensitive. So there are all these different experiments. All these different lines are different experiments. Okay. And if the interaction level is larger than some number, then the experiment can detect it. It's designed to be sensitive at that level. If the interaction is smaller than that, then the experiment cannot detect it. So what the experiment does is set what is technically called an exclusion limit. These are in some sense equivalent of annual reports of companies. You give at the end of the year, what have you done? What is your profit and loss? This is the profit and loss statement of an experiment. It tells you where do you stand today, what will you do in 1 year's time. If you were here in 2012 in this experiment, this was Xenon 2011, this one is the same experiment Xenon in 2012. You've changed by a factor of 10, you've improved your sensitivity by 1 order of magnitude by a factor of 10, great progress. By now actually we've come down 4 orders of magnitude. This is an old plot, I don't know why I didn't use the new one. But this experiment called Xenon has now gone 10 to the power 4 times below this number. So what it is saying is that there are all these different experiments which are trying to look for dark matter, and so far most of these experiments have essentially not found anything and have ruled out all these cross sections or interaction squares. Okay? So there are exceptions, and again this is something that I want you to notice, that there are these other blobs out there. So sometimes what happens is one of these smaller experiments will observe a signal. They think that they have observed some events which are above what they would call their background. Then you claim a signal. So these experiments claim the signal, these 3 blobs or 4 blobs here. But as you see that these blobs are in a region which are excluded by the other experiments. This happens in science. Sometimes experiments see things to the best of their ability, they try to remove all sources of noise and uncertainty. But they, in the end, being scientists, we cannot wish away something. So if we see a signal, we have to report it. So we report it. To our unhappiness, our competitors then do a better job of the experiment and show that our signal could not be right. So it's egg on the face sometimes, but it's part of science that you do the best job that you can. Sometimes you are wrong. Others, figure out that what you had seen was some dirt. Okay, that's what happened for these experiments. So this happens again and again. So you might have heard in the media news stories of some bicep experiment which saw some gravity waves, B modes in the sky, and it turned out to be dust in the galaxy. Or for example, this faster than light neutrinos which were later proven to be just some cable which was loose. This is part of science. We try to do the best job that we can. Sometimes we are not good enough. Okay? So I want you to also appreciate this factor. Science is a human endeavor. It has exactly the same problems as any other field of activity by humans. We make mistakes, but we try to be honest about it. When we make mistakes, we say that yes, this is the mistake that we made. Alright, another way of detecting dark matter would be that there is dark matter out there in a galaxy. There is Earth with satellite around it, and dark matter in the galaxy annihilates with each other and produces some other particles which we can now detect. Sorry. So this dark matter particles annihilate, they make some particles, let's say electrons, and then this electron can then be detected at our satellite. So this is known as indirect detection, because now the dark matter particle did not actually come to my detector. It's only being indirectly detected. So there's all these different ways of detecting dark matter. There are many experiments. As I also for this studies, you can look at many different kinds of sources with many different kinds of experiments. So there are literally of the order of 100 experiments which are looking for dark matter at this time, with many different ways. So far we haven't found any evidence for dark matter. So that's a depressing state of affairs. But there is good reason to believe that we are actually getting to a point where things are going to get interesting. Okay? So the reason is that there is a very good reason to believe that the level of interaction between dark matter and ordinary matter should not have been far above this line that is shown in all these. This flat line. Okay, so there is some theoretical reason to believe why the interaction strength should be what this line is. And for the longest part, we were looking at this region where we don't actually expect to see anything. But we needed to do that in order to develop technology to get to a point where we would start looking at this. Now we are beginning to look at certain experiments where we are going below this line. And this is interesting. If we rule out all of these things, then that would be very interesting. That we go through all of those things and don't find dark matter, then that's a problem. At least for this class of models. There are other class of models which probably fail. So that's the story of dark matter searches. There's yet another, just to give you a sense of this, is full variety of models. So let me stop there. So there's also LHC which is looking for dark matter. You could produce it. I'm not going to go into it. There's lots of other things you can do. You can look at the shapes and structures of galaxies, which also tell you something about dark matter. In this case, not just the gravitational effects of dark matter, but imagine dark matter to have a little bit of pressure. The dark matter, just like ordinary matter, interacts with photons a little bit. Whatever is allowed by data. And that has some tiny effect on the structure and the number of galaxies. You go and measure this very precisely, which has not been measured yet. And then you try to say something about that. So all I'm trying to say is that there are like 100 different ways of looking for dark matter. They rely on many different techniques. Just to give you a sense of, there's many different approaches, many different groups which are trying to do this. And with that, I'll leave you with my final message. That there's overwhelming evidence for this invisible mass in the galaxy. This evidence is incontrovertible. But the flip side of this story is that we don't know what this invisible mass is made of. We're trying very hard. There are hundreds of experimentalists, thousands of experimentalists, a few hundred theorists who are trying to solve this problem all over the world. We've been doing, I think, in great earnest this whole thing for the last 20 years or so, maybe 15, 20 years. Although this has really picked up in the last 5 or 10 years. Most people in the community believe that we will see something over the next decade or two, but there are no guarantees. Okay? So with that, thanks.
One brief question, sir. I got wavered between dark energy and dark matter. Both have a gravity effect. How do you separate them?
Yes. So
Let me add to that question. Just adding to this question, what is antimatter?
I will talk about that, but have you finished the question?
The question is finished.
Yeah. So what is the difference between dark matter? These are similar. I'll get to you in a second. Dark matter and dark energy are different in the way that dark matter forms blobs. Dark energy does not form any blobs. It is completely uniform over the entire universe. Okay? What is antimatter? antimatter is not as exotic as dark matter. We have seen antimatter, we can produce antimatter. Antimatter is just, take any known particle like an electron, it is exactly the same thing with the charge flip. It has the same mass as this object and the charge is the opposite. So for example, if you have an electron, you have something called the positron or the anti-electron, whatever you want to call it. It has the same mass as the electron but a plus charge instead of a minus charge. You have a proton, you have an anti-proton. These antiparticles have been observed and we create them routinely in the lab.
And it exists in the universe?
And see, the thing is that antimatter can interact with matter and annihilate. So it's very hard for it to exist for too long or in too larger quantities because they always find partners to annihilate against. But that does not mean that they don't exist at all. So there are small fluxes or say populations of antimatter going around, whizzing around in the universe. We can detect them too. Which one? The antimatter? Because it's boring. Because because all we have to do is that take that picture and basically make a copy of that picture next to it. Everything is exactly the same. So why say the same thing twice? So it's like the periodic table of elements where you see, for example, the lanthanides and the actinides are often not expanded out because in some sense for chemists, all of those elements are the same. They have the same properties. We are roughly, with the same philosophy, not talking about many of, actually the particles that I showed, they're not all. There are some particles among them which actually come in 3 colors. And I don't show you all the 3 colors, I just show you one of them representative because we know that all 3 of them are just copies of each other. So,
what if this dark matter is not like any known particle made of any...
It's possible. I mean, this is a very interesting, somehow this is a question that everyone asks when they start. So when I was, so I didn't start out by learning about dark matter. I was working on these supernovas and neutrinos and how stars explode. And at that point I got more interested in dark matter and I started studying it. It's the first question that I asked my then boss who was teaching me more about dark matter, that how do you know that dark matter will have any interaction other than gravity with ordinary matter? How do you believe this, that we are going to succeed in this game? I mean, it might just be that it just lives out there, some particle which only has gravitational interactions and we will never know what it is. It is possible, right? And his answer was yes. But as scientists, we often,
So again we're trying to detect something or measure something by the tools that we know.
yes.
And this may not fit at all.
It may not fit at all, but science often also works by being optimistic. That this is a possibility, but it's a very pessimistic possibility, if you will.
Not at all. I'm saying, shouldn't imagination play a greater part in this? And you know what I'm trying to say. And to accept that our tools are may not be sufficient. They may be
Yes, absolutely. So we are perfectly, aware that this is a possibility, that dark matter is not like one of these other particles. But then, if you stop there, you can't do very much more. So often a good scientist will take this point of view and ask, okay, dark matter does not have any interactions of this kind, can I still somehow find something about it? And they will try to come up with some clever way that, okay, maybe if it just sits there, how is it produced? It has to be produced from something, right? How did the dark matter particle get produced? And so you'll have to come up with some theory. That will give you a backdoor to probe this particle again. So in some way we always, when we are faced with a very tough question like this, that what if it doesn't have any interactions, we ask ourselves, what are the things that it must do? And does that give us some sort of a backdoor into probing it? Often this can be very hard, but that's it.
And what would happen if and when this is solved? when we discover the properties, for
Let's say,
example.
so good, that's a much more optimistic approach. So let's say what will happen. So what is likely to happen? So what will likely happen is that several of these experiments over the next decade or two will start seeing signals. That they see these events of particle collisions in one detector. One detector is made of some particular kind of atom and it starts seeing signals. Another detector made of some other kinds of, let's say, one is made of silicon, the other is made of germanium, and they see signals. And over time, these things build up in strength, we believe the data, and they are consistent with each other. So there would be some very limited class of models which would explain all these different lines of evidence. And then over time we would have a theory for dark matter is. Right? Then you will, maybe 20 years later somebody will come and give this talk and he'll be telling you about the standard model of dark matter where we went through this 20-year period of looking for dark matter. We did these experiments where we found these evidences. Putting all of this evidence together, this is what we think is the nature of dark matter.
And thank you for mentioning Mumbai Local 20 years ago.
So that's what I think will happen. And how does it help? Maybe, is that what you were asking?
No, of course, as knowledge, of course, it takes you further. But is there something else besides that?
It's very hard to say a priori because let's say we talk about something like relativity, Einstein's theory of relativity or quantum mechanics. When these things were discovered, nobody knew what the technological impact of these things would be. Today,
Or even knowledge impact, right? You don't know what the future knowledge impact is.
you have no idea of where this is going to go. And something like relativity or quantum mechanics, now it's so important. You cannot get from your home to this place. I don't know where you live though, but I couldn't have gotten here without the GPS on my phone, which wouldn't have worked without general relativity. Okay, my cell phone wouldn't work. These computers wouldn't work. All of these things require quantum mechanics and relativity.
Yeah, semiconductors. That's what, the problem here is now, all higher physics, you need money to be pumped in because they are very precise experiments which involve. So the world is, the world thinks otherwise, they think that physicists are, as if the poverty of the world would disappear and that...
No, I wouldn't be so negative. I think the taxpayers do their job. I think at least in a country like India, we certainly could be funding science and education more, but I don't think they're doing too bad. Education, I think there should be more money that goes into education.
Oh yes, you are not
Our science funding is not bad.
Anybody's money.
I, as a scientist, I wouldn't complain about the level of funding in science. I mean, it could certainly be better, but given our socioeconomic situation, I think our country supports science at a perfectly legitimate level. This is not true of countries like US, for example.